Good evening everyone, good evening elites, good evening. I welcome you all again to the NEET Elite. Hoping that you guys are doing great, having a good time. Well people, you can let me know in the chat box if I'm audible and visible to everyone. You can let me know in the chat box if I'm audible and visible to everyone, yeah? Just let me know in the chat box with some thumbs ups. Good evening, Gayatri. Hi, Sana. Hello, Abdul. Hi, Sai. Hi, Meghna. Hi, Farooq. Hi, Sahifa. Hello, Ashwarya. Welcome. Hello, Bushra. Welcome back. Welcome back, everyone. Welcome back. Welcome back, yeah? Perfect, perfect. So, people, as you all must be knowing, today it's going to be the fourth session, I guess, yeah? Okay, fourth session from the topic isomerism, right? And in the last session of isomerism, we have covered something called as tautomerism, right? And we'll be continuing with that tautomerism right now in the today's discussion as well. We'll be talking about something called as space tautomerism. Then we'll be talking about the Deuterium Exchange. We'll be seeing the Enol content. Everything will be done in the today's discussion, right? Okay. Yes, there was the problem at the end of the last session of isomerism. Yes. I'll be repeating that. No issues. Chill. Perfect. So, the ones who are new to the channel, for them, let me introduce myself. My name is Wassim Sir, and I'm your chemistry master teacher right here on this NEET Elite channel. And the ones who have not liked the video yet, please do like the video, share the video with your friends, and do not forget to subscribe to the channel as well, okay? And do not forget to hit the bell icon so that you get the notification of every single session which will be taking live on this NEET Elite channel, right? Okay, so people, what we are going to learn today is we are going to talk about space tautomerism, we'll be talking about deuterium exchange, we'll be doing the Enol content as well, yeah? You can let me know in the chat box if you guys are super duper excited about the session. Sai, tomorrow we are going to do the stereoisomerism. Tomorrow we'll be doing that, yeah? Tomorrow we'll be doing that. Well, let me know in the chat box. Let me know in the chat box if you guys are super duper excited about the session so that we can start the session directly without wasting any sort of a time. Yeah? Perfect, guys. Perfecto. Yes, Attar will be doing coordination as well. Next week we'll start coordination, okay? The session which I take in the morning for class 11 students, mostly next chapter for them is going to be the atomic structure, and I want all of you to join in that session as well, okay? So that we can do two sessions parallelly in a day, okay? Perfect. All right. Okay, so people, let's talk about something called as space tautomerism first, okay? Let's talk about this space tautomerism. Okay, if you remember, how did I define tautomerism in the last session? Right? How did we define it? I told you tautomerism, it is nothing, it is just the oscillation of an atom, generally which is H positive, between two polyvalent atoms in a molecule, right? I can say in general as the oscillation of H positive between two polyvalent atoms in a molecule, that's something which we call as tautomerism, correct? And we talked about a lot of different types of tautomerisms, right? Among them, the most important tautomerism was keto-enol tautomerism, right? Okay. Now, people, the tautomerism, I showed you two cases in tautomerism. One was for the diode system and one was for the triode system, right? We used to take H positive out from alpha carbon, if you remember, right? Okay. We used to take H positive out from the alpha carbon. Okay. Now, people, two systems we discussed in the last session. One was your diode, one was your triode system. Remember, whenever tautomerism happens, apart from diode and triode system, that's something which I'll be calling as space tautomerism. What does that mean? How can we understand that? Remember, first of all, whenever you see any sort of tautomerism in which H positive oscillation will be there, right? In any system apart from your diode and triode system, that kind of tautomerism is what we call as space tautomerism, right? Let's try to understand all this in detail, okay? Yeah? Okay, understand, guys. Have a look. This for NEET only, right? This not for JEE. This for NEET only. Just a second, guys. What's happening? Okay. All right. Just a second. All right, people, have a look. This is first of all, what is it first of all? It is a keto form, yeah? It is a keto form right here. What is going to happen? In presence of OH negative, what is going to happen? First of all, look at this carbon double bond oxygen. This is my reference, carbon double bond oxygen, yeah? And the carbon which is attached with this sp2 carbon right here, that means I'm talking about this carbon and this carbon, these are going to be your alpha carbons, right? What was the condition for the tautomerism, if you remember? Your alpha carbons must be sp3 hybridized. But over here, it is sp2 hybridized. This carbon is also sp2 hybridized, right? Okay. So I'm not going to take H positive out from this carbon or from this carbon, right? Now what is going to happen? See guys, look at this position right here. Look at this position. This is a carbon right here, okay? This carbon is sp3 hybridized, right? This carbon over here is sp3 hybridized. What is going to happen? This OH negative, it is going to take one of the H positive out from this position, okay? It is going to take one of the H positive out from this position so that there will be negative charge on this carbon right here, okay? So that, let me make it a little clear, right? This OH negative, it's going to take H positive out, right? So that there will be negative charge on this carbon, yeah? Okay. Now people, can I say over here I got negative sigma pi conjugation? So what can happen over here? What can happen over here? When this OH negative takes H positive out, there will be negative charge on this carbon. Now this negative charge is in conjugation with this pi bond over here. So what is going to happen? Can I say resonance is going to take place? Absolutely, resonance is going to take place, yeah? Now, let me show you all the cases over here in a single step only. See, what is going to happen? This negative charge is going to form a pi bond over here, and this pi bond is going to break in this direction, okay? In one of the structures, you'll be getting, in one of the resonating structures, the same negative charge will come over here on this carbon, okay? Now, at the same time, if you look at it carefully, can I say this negative charge, which is now on this carbon, it is in conjugation with this pi bond as well, due to which just there will be something like this. Resonance is going to take place, and this negative charge at the end will come at oxygen, okay? Now, after that, once you get, what kind of structure you get finally? You got something like this, understand? You got something like this. At the end, you got something like this. Okay, I'm not going to show all these steps one by one. At the end, what you'll be left with, there will be a double bond right here. There will be a double bond. There will be a double bond right here at this position. Yes, okay, and there was already a double bond right here. And over here, there's an oxygen with a negative charge, right? This is something which has happened. Now, people, this molecule, it's going to take what? It's going to take H positive from water, yeah? It's going to take H positive from water. So finally, what kind of a structure you got? You got something like this. Understand, what did you get? You got phenol over here, right? Now people, understand, this was the keto form. Now, which kind of form this is? This is enol form, right? So these are basically tautomers of each other. This first one and the last one, okay, first one and the last one, these are basically the tautomers of each other. And this kind of tautomerism, which does not happen in the diet system or triad system, this kind of tautomerism is what we call as space tautomerism, right? Okay, let me know in the chat box. Let me know in the chat box if it's clear so that I can give you a few more examples. Yes, Aniket, that's in the syllabus. Yes. Physics wala lectures. Yes, you'll be covering everything with me. Relax. Okay, let me know if you got the procedure of how the space tautomerism happens. Yeah. So people, one by one, let me show you again. Yeah. See, first of all, what happened? This OH negative took H positive out so that there was a negative charge over here. Now, this negative charge will participate in the resonance. Okay, so what happens after this? You get the negative charge as this carbon, and finally the same negative charge comes on what? Comes on this oxygen, and this O negative takes H positive from water, and finally you get a structure, you get phenol. Okay, so this one, this keto and enol. So these are basically tautomers of each other. So they are going to remain in equilibrium with each other, right? Okay, this keto and enol form, they are definitely going to remain in equilibrium with each other. Correct? Okay, let's move on. Let me take a few more examples. Say guys, the few more examples of space tautomerism. First of all, look at your reference. What is your reference over here? This C double bond O is your reference, correct? This is my reference. Okay, the carbon attached to this sp2 carbon over here. See, this carbon is sp2 and the other carbons which are attached with this sp2 hybridized carbon, those are what we call as alpha carbons. This is alpha carbon. But is this alpha carbon right here sp3 or sp2? It is sp2 hybridized. So should I be taking H positive out from here? No. This OH negative is not going to take H positive out from here, okay, because it's sp2. The condition is the alpha carbon should be sp3. So H positive is not going to leave from here, okay. Look at the other carbon which is adjacent to it. That means this beta carbon, for example, okay. Right? This is again sp2. Look at the other carbon. This is sp3. Okay. So what is going to happen over here? Understand. Let me erase this part. So you got to know this OH negative is going to attack this hydrogen over here. Okay. So what is going to happen? This OH negative takes H positive out from it. So you get something as CH2 negative. You get something as CH2 negative after H positive leaves. Then there's a single bond. This is going to be CH double bond. This is CH single bond, C double bond O, and this is H. Correct? Now people understand. Can I say this negative charge is in conjugation with this pi bond? Yeah. So my next step is going to be like this. See, this negative charge will come here in the form of pi bond. This pi bond breaks in this direction, right? What is going to be my one more resonating structure? My one more resonating structure is going to be CH2 double bond CH single bond CH with a negative charge on this carbon. Yeah. It is C, this is double bond O, and this is H. Can I say again this negative charge is in conjugation with this pi bond? Correct? So what is going to happen? This negative charge will come here and this pi bond will break in this direction. So my one more resonating structure is going to be like this. This is CH2, correct? This is double bond, this is CH, this will be CH, this is double bond, this is carbon, this is oxygen with a negative charge, right? And this hydrogen. Now what is going to happen? This molecule, okay, this resonating structure, it will take H positive out from this water, right? It will take H positive out from this water and will get attached right here. So finally, you get something like this. You get CH2, right? I'm writing CH2. This is simple double bond, your CH, right? Then single bond CH, correct? Then double bond C, and with this oxygen, hydrogen gets attached, and at the end, you have hydrogen over here. Yeah? Now people understand. See, this was your keto form, right? This was your keto form, and which form is this? Which form is this? This is enol form, yeah? Again, these two are going to be, first of all, what? These two are going to be what? These two are going to be tautomers of each other, correct? They are going to remain in equilibrium with each other, right? This one and this one. These are tautomers of each other, and which kind of tautomerism happened over here? This is basically space tautomerism happening, right? Because the H positive is not leaving from the alpha carbon right here. Okay, yeah, I hope you got the concept of exactly what space tautomerism is all about, right? Remember, whenever H positive does not leave from the alpha carbon position, or you can remember it like this. Whenever you'll be seeing any sort of tautomerism, apart from diad and triad system, that kind of tautomerism is what we call as space tautomerism, right? Whenever H positive will be coming from either beta, gamma, or whatever carbon, that kind of tautomerism is what I call as space tautomerism, right? Let me take a few more examples so that it'll be clear to you. This is one more example, yeah? Now people understand. First of all, find your reference. Find the reference. Find the C double bond O, carbonyl group, right? Find the C double bond O. This is your C double bond O, correct? So this carbon is attached with the sp2 carbon. This carbon is attached with this sp2 carbon. So these are going to be my alpha carbons, right? But are these sp3 hybridized? No, both these are sp2, right? Even beta carbons, these are your beta carbons with respect to this reference, okay? These are again sp2, this is again sp2, this is again sp2, 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 but this is sp3. Right here you have got two hydrogens attached over here, right? This is sp3 hybridized carbon, okay? Now, what is going to happen in presence of OH negative? See, if this OH negative attacks at one of the hydrogen over here, what is going to happen? Hydrogen will leave as H positive, due to which there will be negative charge on this carbon, right? Now this negative charge can participate in resonance, right? This will come here and this pi bond will break in this direction, so that there will be negative charge right here. Then this negative charge will again participate in the resonance. There will be negative charge on this carbon, right? Then this negative charge will participate in resonance, yeah? So there will be negative charge on this carbon. Then this negative charge participates in resonance again, so that at the end you get the negative charge on oxygen, right? And once negative charge comes on oxygen, what is going to happen? What is going to happen? This negatively charged oxygen is going to take H positive from water, and at the end, what do I get? At the end, what do I get? Let's try to make that. Let's try to make that, yeah? See, the final structure I'm going to make. The final structure I'm going to make, yeah? See guys, let's make it properly. First of all, over here you'll be getting a pi bond. Over here you got a pi bond, right? Over here you got a pi bond. Yes, you got a pi bond over here, and one pi bond was already here, right? Okay, this pi bond is going to break in this direction, so there'll be a single bond now, right? Okay, and at the top you have got the one more benzene kind of a ring, right? It's going to be like this, right? And on what positions there will be double bond in this ring? See, double bond will be right here. This is one double bond. Over here it's going to be one more double bond, right? And over here already there was one double bond, and it's going to be single bond OH. Okay, so these two are basically the tautomers of each other, right? These are basically the tautomers of each other, correct? One was your keto form, and this is now your enol form, right? These are tautomers of each other, so they are going to remain in equilibrium with each other, correct? Right? Just let me know in the chat box if it is clear to everyone. Just let me know in the chat box so that I can give you one more structure. Okay, one more case of the space tautomerism. Just let me know first of all in the chat box if everything is clear so that I can move on to the next one. We have got a lot of things to discuss in the tonight's session, yeah? Okay. Ligashri, day after tomorrow we'll be starting the 2022 batch as well. Just relax. Okay, wonderful guys. Now, let's try to do the same thing with this molecule over here as well. See, first of all, this is my reference. This C double bond is my reference, and this is your alpha carbon, this is your alpha carbon, but both are sp2. I've got nothing to do with them, right? Now people, look at this one. Look at this one, okay? You have got hydrogen right here. If OH negative attacks at this hydrogen, takes H positive out, there'll be negative charge on this nitrogen, okay? Now this negative charge can participate in resonance, right? So that there'll be negative charge on this carbon over here. This negative charge again participates in resonance, so at the end, negative charge will be on this oxygen. And this oxygen is going to take H positive out from water at the end. So what do you get? What do you get at the end? You get OH over here, right? And where all you get the double bonds, you get one double bond right here, one double bond right here, right? It's going to be like this. It's going to be like this, yeah? And sorry, this nitrogen right here, correct? This is nitrogen over here, yeah? So these two are basically tautomers of each other, which are going to remain in equilibrium with each other, yeah? I'm sure it's again clear to you, right? These are these tautomers of each other. Let me know in the chat box if it's clear. Let me know in the chat box if it's clear to everyone. Yeah? Perfect. All right, guys, wonderful. Now let's move on. Let's talk about something called as deuterium exchange, okay? What happens in this deuterium exchange? I'm not going to show you its mechanism, right? Mechanism is based on the same thing, keto-enol transform, okay? Right? Just remember what all things you have to do over here. See, first of all, look here what you have to simply do. This is first of all the keto form, right? This is the keto form. Now in presence of O, till now what we used to do, we used to have OH negative in presence of H2, right? But now I'm going to use OD negative in presence of D2, where D is basically the isotope of hydrogen, right? Deuterium. Okay. Now people, what you simply are going to do is, first of all, with respect to this carbon double bond O, find the alpha carbons. This is the alpha carbon. This is the alpha carbon, right? Okay, whatever hydrogens are attached with the alpha carbons, remove those hydrogens, and instead of those hydrogens, put deuterium. Okay, so what you'll be getting something like this. This is something which you need to remember like this, okay? No need to go for the mechanism and something. Okay, this is going to be, instead of these 3 hydrogens, I'm writing 3 deuteriums, yeah? And instead of these 2 hydrogens, I'm writing 2 deuteriums. It's going to be CH3 over here like this, okay? Right? So this is something which you'll be getting. This is something which I call as deuterium exchange, right? When your alpha hydrogens are replaced by your deuteriums over here, okay, this kind of exchange of hydrogens by the deuteriums is what we call as deuterium exchange, right? Now people, if you look at the second example, okay, one thing you are going to remember is, you are going to take alpha hydrogens, you are going to take hydrogens out from the alpha carbons, point number 1. Point number 2, if there were no alpha hydrogens, what you are going to do at that time? Understand, guys, properly understand. Properly understand. Tesla, I'm not getting what you're saying exactly. Can you just tell me again what you're talking about? Okay, look here, guys, look at one more example. See, first of all, see, this is C double bond O, correct? This is my reference. Now, this carbon, it's my alpha carbon, right? But it's sp2, nothing to do with this. It's sp2, nothing to do with this, right? Beta carbon, this is again sp2. This gamma carbon, this sp3. So what I'll be doing right here is I'll be taking one H positive out, okay? I'll be taking one, see what I'm going to do exactly. I'm taking one H positive out from this position. So there'll be negative charge on the carbon right here, yeah? So there'll be negative charge on this carbon right here. So in one of the structures, you get negative charge on this carbon. Now this negative charge participates in resonance, right? Okay, like this. In another structure, in another resonating structure, you get negative charge on this carbon, right? In another structure, you got negative charge on this carbon, right? Now, in one more structure, you are going to break this, like this, yeah? So that at the end, you get negative charge over here, correct? Now, we will see which all carbons got the negative charge. Carbon number one, this carbon and this carbon, right? These two star carbons, these got the negative charge, right? So what you'll be doing over here is, you'll be taking the hydrogens out from all those carbons. You'll be taking hydrogens out from all those carbons which got the negative charge due to this resonance, yeah? And you are going to replace those hydrogens simply by deuteriums, right? So you are going to replace these 3 hydrogens by 3 deuteriums. You are going to replace this single hydrogen by a single deuterium. So what you'll be getting at the end, you get same like this, CD3 instead of H3, CD3, right? It's a single bond. This is CH, nothing to do with this, right? It didn't get the negative charge, right? Even this carbon got the negative charge, okay? And with this carbon, you had one hydrogen attached. So instead of that one hydrogen, I'm putting deuterium, okay? Rest everything you're going to keep same, okay? I'm sure it's clear to everyone, right? Let me know in the chat box if it is clear to everyone. Let me know in the chat box if it's clear to everyone, yeah? So point number 1, replace the alpha hydrogens. Replace the alpha hydrogens by deuteriums, okay? Point number 1. Point number 2, whatever carbons will get negative charge due to resonance, replace the hydrogens which are attached to those carbons, replace those hydrogens from deuteriums. As simple as that, yeah? You'll be getting the product, okay? Let me take a few more interesting examples, yeah? This is something which we formed just, okay? Let's talk about this one. Let's talk about this one. See, first of all, it's again the example of the deuterium exchange because you are doing it in presence of OD negative in presence of D2O, right? It used to be OH negative in presence of water, but this is OD negative in presence of D2O. So what you guys will be doing over here is, see, first of all, if I ask you, this is your reference, this is the alpha carbon, this is the alpha carbon, but both are sp2. Even these two are sp2, but this is sp3. Right here, you have got 2 hydrogens attached, okay? You have got 2 hydrogens attached, right? If one of the hydrogens leaves as H positive, there will be negative charge on this carbon, right? Now, this negative charge, this carbon, this is in one of the, in the first step, what you'll be getting negative charge on this carbon. Now, this carbon carrying the negative charge, this negative charge is going to participate in the resonance. In the second structure, you get negative charge on this carbon, yeah? Similarly, this negative charge was in conjugation with this one as well. So one more thing would have happened. It would have come here and this bond would have broken in this way so that there would have been negative charge on this carbon, right? So which all carbons are getting negative charge? I'll say this carbon number, for example, 1, carbon number, let's say this is 2, let's see. These 3 carbons are getting basically the negative charge, right? Over here, with this carbon, how many hydrogens are attached? 2. So instead of these 2 hydrogens, you are going to attach 2 deuteriums, right? Okay, how many hydrogens are attached with this carbon? There is 1 hydrogen attached, okay? So instead of this hydrogen, you are going to attach 1 deuterium, okay? Over here, again, you have got 1 hydrogen attached. So instead of this hydrogen, you are going to attach deuterium. So what is going to be the final structure which you got? You got something like this. You got something like this. You're doing nothing with the structure. You are just replacing whatever hydrogens I told you, right? These 2 hydrogens by these 2 Ds over here like this, yeah? And 1 D over here, 1 D over here, like this. Correct? Okay, this is something which we call as deuterium exchange, right? This is one of the common example of it, right? Similarly, let me take a few more examples. This is one more example, and I'm sure you're going to kill it now, yeah? If you got the concept, you can do it properly. First of all, I need to have a look on those carbon atoms which will get the negative charge if H positive leaves. First of all, H positive leaves from which position? H positive cannot leave from here because it's sp2. This is sp2. Every carbon is sp2 apart from this. This carbon is sp3. So hydrogen is going to leave from this position. Yeah. Then there will be negative charge on this carbon. Right. Now this negative charge, it can participate in resonance in this side as well on this side, because this negative charge is in conjugation with this pi bond as well as this pi bond. When this negative charge participates in conjugation with this pi bond breaks in this way, so that there will be negative charge right here. Okay, when this pi bond, okay, when it participates in resonance in this direction, there will be shift of this pi bond in this direction, so that there will be negative charge right here on this carbon. Yeah. Now after this, see again, either this negative or this negative. Choice is all yours. Let's assume this negative charge, it's in conjugation with this pi bond as well. So it can come here, this pi bond can break in this way, so that will be negative charge on this carbon, right? Now this negative charge, which is present on this carbon, it's in conjugation with this pi bond as well as this pi bond. Okay, break any of one, right? Just shift the pi bonds like this. There'll be negative charge right here. One more thing would have happened. This negative charge is in conjugation with this pi bond as well. Okay, it could have shifted in this way, and this pi bond could have shifted in this way, so that there could have been negative charge on this carbon, right? And this negative charge finally it's in conjugation with this pi bond, correct? Now which all carbon atoms are there which got the negative charge? See, this carbon atom, 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 this carbon atom. Okay, all these carbon atoms got the negative charge. Now people, what is going to happen? Understand. You're going to remove all the hydrogens, okay, all these starred hydrogens, right? Where I gave the star sign, you're going to remove all the hydrogens which are attached to the carbons containing the negative charge, right? And you're going to replace those hydrogens from by these deuteriums, okay? Now, first of all, over here we have got two hydrogens attached. So in place of these two hydrogens, you are going to attach two deuteriums. Right here, you have got one hydrogen attached. So you'll be replacing that by one deuterium. Over here, again, one more hydrogen, you'll be replacing it by one deuterium, okay? Right here, there is no hydrogen attached, so nothing is going to happen at this position. Anyways, it got the negative charge, but nothing is going to happen because it does not have any hydrogen attached. Its valency is always, it's completed, right? It's not attached with any of the hydrogens. Now this carbon, it's attached with one hydrogen, replace that one hydrogen by one deuterium and replace this one hydrogen by one deuterium as well. So how many deuteriums you are going to attach? 2, 3, 4, 5, 6. So you are going to attach 6 deuteriums right here. Okay. So finally, what will I be getting at the end? I'll be getting something like this. See, I'll be getting something like this. Understand? Nothing to do with the structure. Keep these pi bonds as such. Okay. And at the top, you had oxygen, right? Keep this double bond in between as such, right? And in the bottom, you are going to do nothing till now. Okay. Just keep these pi bonds, right? Now, over here, you are replacing two hydrogens by two deuteriums. So one deuterium on this side, one deuterium on this side, for example, right? Okay. One deuterium you are going to add here, one here, right? So one deuterium here, right? What all positions are there? This one and this one. Just attach one deuterium right here, one deuterium right here. This is the final structure which you got, and this kind of exchange is what we call as deuterium exchange, right? So you attach 6 deuteriums instead of 6 hydrogens. Yeah. Is it clear to everyone? Can you let me know fast? Can you let me know in the chat box if it is clear to everyone? Yeah. Sakti, the next is going to be coordination chemistry. First of all, we'll finish off this isomerism, hydrocarbon and solutions, right? Because all the three are going parallelly, correct? We'll try to finish them all first. All right, wonderful. Let's move on to a few more interesting things. Okay, this is one more example, right? Okay, you can do it. You can do it, guys. Okay, you're going to do the deuterium exchange, but you need to be careful with certain things. You need to be careful with certain things, right? First possibility. From where all positions I can take H positive out. See, this, first of all, select your reference. This is C double bond O, your reference. Right? This alpha carbon, right? But this is sp2, this is sp3. So you can take H positive out from here so that there'll be negative charge, right? There can be negative charge on this carbon, correct? Okay. You can take H positive from here as well. Therefore, there'll be negative charge right here. Okay. You can do that. Yeah. Now people understand what is going to happen. Even you can take H positive from here as well so that there'll be negative charge right here on this carbon, right? You're just saying one thing. You're just saying what all carbons will get the negative charge, right? Now let's check the conjugations. Let's check what all possible conjugations are there due to which there will be negative charge on the carbon atoms. See, this negative charge due to conjugation, it can break this pi bond in this way, so that there will be negative charge right here on this carbon as well. Yeah. Now this negative charge either or this negative charge. Okay, both the ones are in conjugation, so just take one of them. There will be negative charge right here. Okay. Now people, one more possibility is this way. One more possibility is this way. Negative charge on this carbon, right? Okay, I think we are done, right? See, how many hydrogens are attached right here? There are 2 hydrogens attached. Okay, so you are going to replace these 2 hydrogens by 2 deuteriums, right? Over here, again 2 hydrogens were attached. You are going to replace them by 2 deuteriums, right? Over here, 1 hydrogen, you are going to replace by 1 deuterium, okay? See, right here, there is no hydrogen attached, so nothing to do with this. Over here, you have got 2 hydrogens attached, so replace them by 2 deuteriums. 1 hydrogen attached, replace them by 1 deuterium. So total, how many deuteriums you are going to attach? 2, 2, 4, 5, 6, 7, 8, right. 8 deuteriums you are going to attach right here with the molecule, okay? Right? Right. So finally, what you'll be getting? You'll be getting something like this, yeah? Right? 2, 4, 5, 6, 7, 8. So you have attached 8 deuteriums right here with the molecule. Exactly. Let me know in the chat box if it is clear to everyone. Yeah? John Victoria, just drag the video a little back. It'll be a replay for you, okay? Just let me know in the chat box if it is clear so that I can move on. Let me know fast. Perfect, guys, okay? Now, let's move on to something called as Enol content, right? Enol content. Well, people, we have discussed in the same Toutomerism. See, I'm going to talk about a special type of Toutomerism, the important Toutomerism that's in your syllabus. That's keto-enol Toutomerism, right? That's something which we have discussed, but there are a few more points in this keto-enol Toutomerism, right? Due to this Toutomerism, this keto and enol, they stay in equilibrium with each other, if you remember, right? They stay in equilibrium with each other, correct? So basically, this is something which is happening in the container. So in the container, this keto and enol, they are in equilibrium with each other. Now at equilibrium, what is the percentage of enol, right? Basically, at equilibrium, I got a mixture. Containing keto and enol. I have got the mixture at equilibrium containing keto and enol form. Now, what is the percentage of enol in that equilibrium mixture? That's something which we call as enol content, right? If the percentage of enol in the equilibrium mixture is more, I'll say enol content is more. If the percentage of keto in the equilibrium mixture is more, I'll simply say that keto content is more, correct? Simple, you need to remember. During this Toutomerism, this keto and enol, they stay in equilibrium with each other. That's something which I've told you, correct? So you get the mixture at equilibrium containing keto and enol. Now the percentage of enol in that equilibrium mixture gives you the idea about the enol content. More the percentage of enol, more enol content, right? More the percentage of enol in the equilibrium mixture, more the enol content, right? Now let's move on, talk about this enol content a bit more in detail, yeah? See guys, this enol content, it depends on a lot of things. Enol content in the equilibrium mixture, it depends on a lot of things, okay? Before talking about those, I need to tell you a few more important things. See, for example, I have got the open chain keto. This is the open chain keto form, right? Okay, what is going to be its enol form, right? What is going to be its enol form, right? You're going to make the Toutomerism, right? For example, see, this is alpha carbon, both are sp3. Take anywhere, take the H positive out, either from here or from here, right? If I take H positive from here, it's going to be, the keto is going to be like this. CH3, C, this is going to be OH, and this is going to be double bond CH2, correct? This is your keto form. This is your enol form, yeah? So at equilibrium, these two keto and enol forms, they are going to remain in equilibrium with each other in the container. This is something which is happening in the container. So in the container, what you are finding out, you're finding this keto and enol in equilibrium with each other, correct? Now people, remember one important thing. See, whenever you see the open chain keto, right here, okay, showing Toutomerism, remember at equilibrium, the percentage of open chain keto is nearly going to be 100%, and this is nearly going to be 0%, okay? Yeah? When is it happening? Whenever you see the open chain keto in equilibrium with its corresponding enol, okay? Remember, generally, what you are going to remember is this keto, its percentage is nearly going to be 100%. The percentage of enol is going to be nearly 0%, okay? Remember this thing. Where I'm going to use all this, you'll be getting the idea in some time, Okay, but before that, I need to tell you few important things. The enol content, what all things, on what factors it depends. Enol content depends on the stability of enol. More stable the enol, more is going to be the content of enol. More is going to be the percentage of enol in the equilibrium mixture. Point number one. Point number two. More the intramolecular hydrogen bonding in enol. See, once you get the enol, if there was intramolecular hydrogen bonding happening in that enol, okay, remember, more the intramolecular hydrogen bonding happening in enol, more is going to be the enol content, because that intramolecular hydrogen bonding in enol makes it highly stable. Okay. One more thing, aromaticity in enol, right? Due to tautomerism, if enol got the aromatic nature, if enol got some aromatic character, remember that enol is going to be highly stable, and if the enol is highly stable, its enol content is going to be more in the mixture. Yeah, enol content is going to be more in the mixture. Correct? Yeah. Similarly, few more things. Remember, enol content, it depends on the sum of all the bond energies in the enol as well. Remember, more the bond energies in the enol, more the bond energy of the enol, right? More is going to be the stability of the enol, more is going to be the enol content. Remember this thing as well. The most important, enol content, it depends on the stability of negative charge after the removal of acidic H positive as well. Right. See, what we do basically, we take H positive out from the alpha position mostly in the diode and triode system, right? We take H positive out. After H positive goes out, there will be negative charge on the carbon, right? There'll be negative charge on the atom, first of all, on the polyvalent atom, right? Now, depending on the stability of that negative charge on the polyvalent atom, you can talk about the enol content as well. Remember, more the stability of negative charge after the removal of acidic H positive, more is going to be the enol content. Yeah, this is one more point, right? And one more point is, more the extent of resonance in enol, more is going to be the enol content, right? Okay, all these factors you have to take in consideration, then only you can talk about the enol content in the equilibrium mixture, right? Because at equilibrium we have got the keto as well as enol, yeah, okay, and whatever is going to be the content of enol in that equilibrium mixture, we call that as enol content, and that enol content, it depends on these factors. The most important factor is this one. Stability of negative charge after the removal of acidic H positive, because it takes into account majority of these factors, right? So let me give you some examples so that you'll get to know properly what I'm talking about. No, Firuk, no. Just wait for it. See guys, I'm directly starting with the questions. You'll get the clear-cut idea of all these things, okay? Few minutes back, before doing these questions, first of all, these two are tautomers of each other. This is keto, this is enol. This is keto, this is enol, correct? These are in equilibrium first of all. But before doing that, few minutes back, what I told you, whenever you have got the open chain keto, yeah, whenever you'll be having the open chain keto in equilibrium with its enol, remember, the percentage of keto is nearly going to be 100% and percentage of enol is nearly going to be 0%. But right here, is this open chain keto? This is not open chain keto. It's a cyclic keto, right? It's a cyclic keto. Understand what is going to happen. See, first of all, this is your C double bond O. This is alpha carbon sp3 hybridized alpha carbon, right? So it has got hydrogen attached. Take the H positive out, right? There'll be negative charge right here. Right? Now this negative charge is going to participate in the resonance, due to which there'll be negative charge on this oxygen, and this O negative takes H positive from water, so you get something as OH over here and you get a double bond over here, correct? See guys, this is not the open chain keto, this is a closed form keto, right? This is keto and this is enol. Due to the tautomerism, what is happening in enol? Can I say I'm getting something as aromatic compound right here? Yeah, there was no aromaticity in this keto. Because for the aromaticity, what all things are to be satisfied? First of all, there should be the ring, it should be cyclic. This is cyclic, no doubt, right? All the carbon atoms, all the atoms right here, they should be sp2 hybridized, right? This one is not sp2 hybridized. So this is not aromatic at all. But it's getting converted into enol. Check the enol. All the atoms are sp2 hybridized, yeah? There is complete cyclic conjugation and it's following the Huckel's rules as well. There are 4n plus 2 pi. There are total 6 pi electrons participating in the complete cyclic conjugation, right? So once this enol gets formed, this ring becomes aromatic. So the stability of enol is more, if the stability of enol is more, you can clearly say enol content in the mixture is going to be more than that of keto, and it's going to be around 100%, okay, and this is going to be around 0%, right? Why it happened? Because the enol which you got, that's aromatic in nature. If it's aromatic, highly stable, its percentage is going to be nearly 100%, yeah? Okay. Now people, if I talk about this one as well, if I talk about this one, first of all, these two are tautomers of each other, correct? These two are tautomers of each other. We know it, yeah? Okay. Now people understand. Was this ring aromatic? No way. Why? Because this carbon is sp3 hybridized, okay? Over here in this ring, first of all, this is keto, right? This is keto form, and this is enol form. Check this ring, is this aromatic? Understand, every carbon in the ring is sp2 hybridized. There is complete cyclic conjugation as well, right? Okay, now how many pi electrons do we have participating in the complete cyclic conjugation? We have got 2 pi electrons participating in the complete cyclic conjugation. So this is again your aromatic, right? So if it is aromatic, that means this enol which is getting formed right here, it's very, very stable. So its percentage of enol in the equilibrium mixture is nearly going to be 100 right here, and this is nearly going to be 0%. Yeah, nearly is the term which I'm using. Okay, right? Okay, I'm sure it's clear. Let me take few more examples, few more important examples. Understand. First of all, this is the 7-membered ring over here. Again, this is 7-membered ring. Is this keto or enol form? This is keto form, right? This is enol form, yeah? This is enol form, correct? Now from keto to enol, what is happening? See, first of all, is this ring aromatic ring? No, because this carbon is not sp2. What about this ring? Every carbon is sp2, complete cyclic conjugation, right? 2 to 4 to 6. 6 pi electrons, Huckel's rule follows, so this is aromatic. If this is aromatic, what is going to happen? If this is aromatic, what is going to happen? What is going to happen? I'll simply say its stability is going to be more, and its percentage enol character in the mixture is going to be 100%, and it's going to be nearly 0%, right? Yeah? Let me know in the chat box if it's clear to everyone, yeah? I'm sure it's clear to everyone, right? Right. Yeah? Perfecto. Exactly. This one is more stable, yeah? That's why its percent enol character is nearly 100%. Right? Okay. Now people, if you look at this one, see, this is your keto form again, right? This is your enol form, right? Okay. So first of all, this is not aromatic because this carbon is sp3, even this is sp3, even this is sp3, this is sp3. So both these, keto as well as enol, these are not aromatic at all, yeah? Now, on what factor we are going to decide the enol content over here? Look here guys, very simple. See, this is your keto form, yeah? For example, I have taken H positive out from here, right? And that H positive I have attached with this oxygen, and there is a double bond over here. So finally I got enol, something like this. We know how to make the tautomers, right? I'm not going to show it again, how to make the tautomers. We know it. Correct? Okay, if you have forgotten something, see, this is the H positive which I'll be taking out, yeah? There'll be a negative charge on this carbon, this negative charge will come here, this bond will break in this way, and this O negative, you're going to simply attach the H positive which this carbon has lost, yeah? Finally, so you get something as OH, single bond, there'll be a double bond right here, and there is a double bond over here as well. Now people, one important thing, see. Can I say the enol which I got, see this was your keto form, correct? The enol which I got, can I say there is a possibility of hydrogen bonding? See, this is OH. If I write it like this is OH, correct? Can I say there is a possibility of hydrogen bonding right here between oxygen and hydrogen? And if there will be the possibility of hydrogen bonding in enol form, that hydrogen bonding in enol stabilizes it, okay? So it becomes more stable. If it becomes more stable, definitely we know, I have told you, the enol content, it depends on what? It depends on the intramolecular hydrogen bonding happening in enol as well. More the intramolecular hydrogen bonding in the enol, more is going to be its stability. If more is its stability, more is going to be the percentage of enol in the equilibrium mixture. Yeah? So I can clearly say this is more stable, so its percent enol character is going to be 100, and this is going to be nearly 0% over here, right? Let me know in the chat box if everything is clear till here. Correct? So you need to have a look on the intermolecular hydrogen bonding as well. That's what I want you guys to remember. right here. Okay, just take the H positive out from the alpha carbons. I'm going to take H positive out from this carbon, so there'll be negative charge right here. Similarly, take it out from this, there is negative charge right here. Take it out from over here, there'll be negative charge on this one, this carbon, right? Now check the stability of this negative charge. Okay, see, if I talk about this negative charge, can I say this ring, it will show plus I. It will show plus I towards this negative charge, right? It will show plus I definitely. Over here, no effect, yeah. Right here, this benzene ring, it's going to show what? It's going to show minus I effect towards this negative charge, right? And minus effects, what do? They stabilize the negative charge, right? So I'll say negative charge is maximum stable in the third one, followed by what? Followed by the second one, correct? Followed by the first one. This is the order of the stability of the negative charge, and whatever is going to be the order of the stability, whatever is going to be the order of the stability of the negative charge, same is going to be the order of the enol content right here, okay? Right? Let me know in the chat box if it is clear, fast. Yeah? Let me know fast, let me know fast. Let me know fast. Hemant, I'll be doing that as well, no issues, no issues. Right? Darshini, it's normal, cyclohexene ring, correct? It's the alkyl group, you can say. It is the alkyl group, correct? Alkyl group show plus I. Yeah? Perfecto. Let's move on to a few more examples. See, let's talk about these two examples. What is going to happen? Where will be the enol content maximum among the two? Where will be the enol content maximum among the two? See guys, understand. First of all, select your reference. This is the reference. Okay. Select the reference right here. This is the reference. Okay. Right. Now, just take this H positive out. There'll be negative charge on this nitrogen over here. Take H positive out. There'll be negative charge on this nitrogen. Correct? Yeah. Or let's try to make it like this. See. First of all, these are keto groups. I'm going to make their corresponding enols, right? So take the H positive out and attach this H positive right here, correct? There'll be a double bond over here on this position, right? We know how to make enols, correct? So I'm going to make the enols first. This is nitrogen. It's going to be like this, correct? This is going to be the enol. This is going to be the corresponding enol of this keto. What about the corresponding enol of this one? It's going to be simple double bond right here, right? It's going to be like this. This is nitrogen. Double bond over here, and this is OH, correct? This is the corresponding enol of this keto, and this is the corresponding enol of this keto, correct? Okay. Now, which enol is more stable? Just have a look. Can I say this pi bond and this pi bond, they are in conjugation? They can show resonance, and wherever there is resonance, stability will be more. So definitely percentage, enol content in the first one is going to be greater than that of second one. Yeah, this is going to be the order. Yeah. Because of the conjugation, first one, the enol of the first one is more stable than that of the second one. So I can say the enol content in the first one is going to be more than that of the second, as simple as that, right? Yeah. Or you can decide on the charge as well, right? You can decide on the stability of the charge as well. You can do that now, okay? Now, this is one more question. These are two more questions and you guys are going to give it a try. Very simple questions. I'm sure you all are going to do them. Arrange the following on the basis of the enol content, right? Okay. See guys, first of all, if I make, what do I need to do? Can you let me know what do I need to do? See, first of all, this is the keto group. This is again the keto. This is again the keto. I'm going to make their enols first, right? And what is the first step in making the enols? We take H positive out from the alpha carbon. So when I take H positive out from the alpha carbon, there'll be negative charge on this carbon. Similarly, there'll be negative charge either on this carbon or this carbon. Choice is all yours, right? Similarly, there'll be negative charge on this, for example, this carbon, correct? Okay, right? When negative charge will be on this carbon, then it can show resonance, so that there'll be a pi bond right here, and this will be OH, this will be OH finally. Or you can make their corresponding enols as well, okay? If I make the corresponding enol of this keto, it's simply going to be like this. This is something which I've shown you a few minutes back only, yeah? This is something which I've shown you a few minutes back only. This is OH, right? And this is double bond O. This is the corresponding enol of this keto, correct? Can I say over here resonance is going to happen, right? By not resonance, hydrogen bonding. Intramolecular hydrogen bonding is going to happen in this enol, right? And intramolecular hydrogen bonding in enol stabilizes it, right? So percent enol character is going to be, percent enol content is going to be maximum in the third one. right? Because its enol is maximum stabilized by the intramolecular hydrogen bonding. Yeah, okay. Now people, leave the third one aside. Now talking about the first and second. See, this negative charge on the carbon, negative charge on the carbon, right? Over here, this CH3 will show plus I effect. Right here, you've got hydrogen. It's not going to show any sort of effect, right? Okay, and negative charge is destabilized by plus I effect. We know it. So the stability of the negative charge on the first carbon is going to be more than that of the second one, right? So after 3, what will come? First will come, then 2 will come. This is going to be the stability order, right? 1, the negative charge on this carbon is more stable than that of the negative charge on this carbon, and enol content depends on the stability of negative charge after the removal of H positive, right? We know it, correct? So I can clearly say enol content of the first one is going to be greater than that of the second one, yeah? Right? Similarly, if you look at this example, see, what I'll be doing first of all, these are all the keto groups, C double bond O, C double bond O, C double bond O. These are all the keto groups, right? Let's make their corresponding enols first. Okay, so what is going to happen? In the first case, there will be what? Which kind of tautomerism will follow the first one? It's going to follow the space tautomerism, right? I told you a few minutes back only, correct? You are going to take the H positive out from here, right? There'll be a negative charge right here. This negative charge will take part in the conjugation. Then there'll be negative charge right here. This negative charge will take part in the conjugation. Then there'll be negative charge on this oxygen. And this negative charge is going to take H positive from water. So finally, what kind of enol I'll be getting? I'll be getting phenol as the final structure. So these will remain in equilibrium with each other, right? These are going to remain in equilibrium with each other, correct? This is keto form and this is the enol form, correct? Now in this one, what is going to happen? Take H positive out from here. So you are getting the corresponding enol like this. You are going to get the corresponding enol like this, right? In the second one. In the last one, take the H positive out, right? You are going to get one double bond either here or here. The choice is all yours. It's going to be like this. Right? Now people, you can clearly say which one is more stable, right? You can clearly say which enol is more stable. See, over here, the enol has got some aromaticity, right? 6 pi electrons participating in the conjugation. Right here, is it aromatic? It's not aromatic, but there is conjugation between this pi bond and this pi bond, right? Pi, sigma, pi. Over here, there is no conjugation, correct? So maximum stable is going to be this one. The first enol is going to be maximum stable, followed by second enol, followed by third enol, correct? And stability of the enol is directly proportional to the enol content. So enol content is more in the first one, followed by second one, followed by the third one, right? Let me know in the chat box if it is clear to everyone, yeah? Let me know in the chat box if it is clear to everyone. Let me know in the chat box fast so that I can move on and talk about the effect of solvent on enol content. Let me know in the chat box fast, yeah? Perfect, guys. All right, wonderful. Dinesh, hydrocarbons is not over yet. It's not over yet. Okay, so let's move on then. Yeah? Let's move on. Okay, let's talk about the effect of solvent on enol content, right? First of all, look at this statement. Keto forms enol in order to make hydrogen bond, which in turn increase the stability of ketones. Guys, there is one theory which says keto gets converted to enol only in order to make hydrogen bond with enol, because hydrogen bonding stabilizes keto. Okay, what does that mean? See, first of all, this is the keto form, right? This is the keto form, correct? Okay, this is C double bond O. Just fix it as your reference. This is alpha carbon. Take one of the alpha carbon out. So you're going to get the enol like this. This is going to be the corresponding enol, correct? This was keto, this is enol. Right? Okay, or if I just reverse this enol like this, wait, let me make it like this so that will be more clear to you. See, this is OH, single bond, this is C, this is double bond, for example, CH2, this is single bond, CH3. This is your enol, correct? So when keto got converted into enol, can I say this oxygen and this hydrogen, they are going to show what? They are going to show hydrogen bonding, correct? One of the theories says keto gets converted into enol just in order to get the intermolecular hydrogen bonding, because intermolecular hydrogen bonding, it simply stabilizes this keto group. Okay, there is one theory which says like this. Okay, keto forms Keto forms enol in order to make hydrogen bond, which in turn increase the stability of keto, right? For example, like this, okay? Now, people, few important points, understand. We are basically talking about the effect of solvent on enol content, right? Okay, if I'll use the polar solvent, what will happen? If I'll use the non-polar solvent, what is going to happen? See guys, first, if I do the tautomerization right here in presence of the polar solvent like water, okay, as I told you, one of the theories simply says what? One of the theories says keto forms enol just to make hydrogen bond with the enol, correct? So this keto right here, it will definitely love to form the enol, right? So that it can show hydrogen bonding with that, correct? Yeah? Okay, so definitely it's going to get converted into enol. But the percentage of enol is 16% over here. Percentage of enol is 16%, right? Okay, why the percentage of enol is less than 50? Why is that? Why is that? Right? Why is that? There'll be a reason for that. See guys, understand properly what I said. First of all, isn't this the open chain keto? This is the open chain keto, correct? This is the enol form. Few minutes back, I told you, if you remember, if you'll be having open chain keto, right? The percentage of this open chain keto is nearly 100%, right? And percentage of enol over here is nearly 0%, right? But what is happening? The percentage of enol right here is 16%. Why is that? Because when it gets converted into enol, that enol can form hydrogen bonding with it, which stabilizes it. That's why enol is getting formed. But the point is, why enol is only 16%? Right? Why enol is only 16% over here? Because you are using the water as the solvent. Water itself can make hydrogen bonding with this one, right? Which decreases the formation of enol, which decreases the further formation of enol. That's why your enol content right here is less than 50%, which is your exact 16%. Yeah, I hope you got it. See, normally what should happen? See, this is open chain keto, right? I told you the percentage of open chain keto is 100%, right? And percentage of its corresponding enol is nearly 0%. But right here in this case, the percentage of enol is 16%. That means enol is getting formed. Why? Because as one of the theories says, keto gets converted into enol so that it can form hydrogen bonding with that enol, which stabilizes the keto, right? Okay, that's why enol is getting formed right here. Then the point is, why only 16% of enol is getting formed? Why not more than 50%? The point is, I'm using the polar protect solvent. I'm using the polar solvent water. And this water has got the capability to form hydrogen bonds with this keto right here as well, due to which more keto does not get converted into enol. That's why the percentage of enol right here will be simply 16%, right? Right. Perfect. Now people, the point is, if I'll use non-polar solvent, if I'll be not using the water, then more and more enol will get formed. And the percentage of enol is going to be 76%, right? Okay, it's going to be more than 50 because there is no water which would have formed hydrogen bonds with keto, right? Okay, so remember, when I'll be using the non-polar solvent, the percentage of enol is simply going to be 76%. And when I'll be using the gaseous state, and in case if the solvent is in gaseous state, okay, its enol content is going to be 92%, right? Let me know in the chat box if you're clear with all this. Just remember this statement, enol content is generally higher in non-polar solvents, right? Okay, because in polar solvents, what happens? Hydrogen bonding takes place, which stops the further conversion of keto into enol, yeah? Okay, Rocky, what are you saying? I think you're new to the channel. This channel is for the people who study honestly, okay? You can go to some other channel if you want to have some chit chat, not here. Right? Go to some other channel. Do not spam like this. I do not encourage people who keeps on spamming all the time. You can go to some other channels as well, where you can do the chit chats and all. Not here. Perfect. So people, with this, I'll end the session. Right? With this, I'll end the session. I hope you would have got all the information, right, which I gave you in the today's session. And if you remember, we started with something called as space tautomerism. After space tautomerism, we covered what? We covered a lot of things, yeah? We covered a lot of things in the today's session. We talked about enol content, right? Everything was discussed in detail, yeah? Shiva, coordination chemistry will be, reaction mechanism will be done just after this, okay? Just after this, right? Tomorrow we are going to start the stereochemistry, yeah? Basically, stereoisomerism we are going to talk about in the tomorrow session, right? And the ones who have not joined in the crash course here, guys, please do join into the crash course. It's going to be highly beneficial, trust me on that, okay? because this is the last option for you. This is the last option for you, right? Do get enrolled in this one because your entire course is going to get covered just in 120 sessions. And apart from that, you have got some test series, mock tests, everything is included, right? Everything is included, yeah? And no need to worry about there'll be some sessions with the experts who will keep on giving you the tips and tricks by means of which you can solve the questions in lesser time. Everything will be done in detail, yeah? And how to join into the crash course, you need to click on the Vedantu app, download the Vedantu app. After clicking on it, just click on the NEET crash course. Once you click on the NEET crash course, use the coupon code as WSNET, you get the 30% off. And I'll be training you personally if you are using this coupon code, right? And the link is, there is a link in the description box of the video as well. You can click on the link, get added to the description box, get added to the Telegram group, okay? Get added to the crash course, right? Okay, and the next batch starts on 31st of May. Do that as soon as possible, right? There is a link for the Telegram as well. Click on the link, get added to the Telegram and stay updated about the class. And the ones who have not liked the video yet, please do like the video, share the video with your friends, and do not forget to subscribe to the channel as well, yeah? Thank you, Rohit. Usha, I keep on coming on this channel regularly at 7 p.m. every day, okay? And in the morning at 10:30 for class 11th students. So I've just entered into class 11th, yeah? Okay, chalo, I'll see you guys tomorrow at the same time. Okay, I'll see you guys tomorrow. Tomorrow we are going to start the stereoisomerism. Till then, you guys take care. Bye-bye. God bless you all and love you all. Take care, guys.